Welcome. Today's notes worksheet is entitled Composition of Functions. When you worked with functions in Algebra 2, you probably combined them 5 different ways. One was addition, one was subtraction, one multiplication, one division, and then a 5th way to combine two functions together was by what's called a composition. And so that's the one we will revisit here today. We'll go ahead and just sort of revisit some ideas, the concept behind it, and then go ahead and dive into some of the functions here that we'll combine together. So let's give it a try. At the top of your page here, just sort of a review question. What does composition of functions entail? And if you remember, this was the one out of the 5 operations that you performed that you cannot perform on numbers. You can only perform on functions. And it goes with inputs and outputs. And here's what I have on my paper. Basically, the output of one function becomes the input of a second function. So let's get that piece in there. And we'll go ahead and diagram this out momentarily. Let's just get this in quickly, though. There we go. Something like that. And so I guess what we'll take a look at on your notes worksheet first is sort of the notation that goes behind it. And then as it says, we're going to illustrate this with a little flow chart. So I guess the first order of business is to review the notation that you saw last year in Algebra 2. Just depending on what your Algebra 2 teacher presented to you, 2 ways to express a composition. This open circle right here, it's not multiplication. It does mean composition. So this would read f composed of g of x. And then also this one over here, and primarily I will use this one, so I'm going to go ahead and box that up, although again these two mean the exact same thing. But this would basically say, again, and we'll write this in momentarily, function f composed of g of x. And as a matter of fact, let's go ahead and sort of read it exactly as that. So I'm going to put quotes just as that's how I would read it. So it would be f composed of g of x. So g of x is going to be a particular output, and that becomes, as you can see, the input of the f function. So the output of one function becomes the input of a second function. And in this over here, again, so many different ways to combine functions together. This would just be another alternative to it. And so this would be g composed of f of x. Let's go ahead and write that in as well. So g composed of f of x. All right, nice. Now, again, what we could do is illustrate a variety of different combinations here. I'm going to do this one. This is probably the most prominent one that we will see, f composed of g. And so why don't we go ahead and kind of start that out and see what it would look like, and then sort of go from there and use some functions for it. So anyway, if you would please, can you go ahead and start with your basic input there? So your generic input x. In fact, I'll go ahead and write that in. And so remember how functions work. An input goes into a function, basically. So I'm going to try to do this little function machine, which I can never draw very well. But this would be function g. And so x goes into function g. And remember, a function is just a set of rules that tells us what to do to the input. So function g tells us what to do to the input. And after it manipulates the input, out pops the output. So we get g of x. So input produces output. By now we're pretty comfortable with that piece. Okay, good. Now it doesn't actually stop there. That g of x goes further. So as the little definition up above suggests, the output of one function then becomes the input of a second function. And you can kind of see that. That's why I like this notation right here. G of x then becomes the input for the f function. So you have f composed of g of x. And so let's go ahead and put that in place. So that now travels into this function right here. We'll call that function f. F manipulates it, tells us what to do to that, and then out pops up the final output, which would be f of that g of x. And so there you have it. Nice looking diagram as to how that plays out, of course. And again, probably have some background with this last year in Algebra 2 working with this. We won't do the addition, subtraction, multiplication, or division, but I like this 5th operation, this composition. All right, so let me head to my next board here, and let's go ahead and just try some out. Just kind of get comfortable with that piece. And we'll start with some relatively easy families of functions here. I've got a linear family, so f of x is 3x minus 1. And then how about a quadratic family? G of x is x squared minus 4x plus 8. So again, all different combinations. Let's go ahead and play out A through E here as best as possible. So let's take a look at letter A. It says f composed of g of x. So basically what that means is g of x becomes the input of the f function. So if you take a look on your sheet here, the nice thing about this is g of x is defined for us. This is g of x. That is the function itself. When I put an input in, these are the function rules that give us the output. So this is the function. And very simply what that does is that becomes the input of function f. So it would replace all the x's of the f function. And so that's what it would look like in essence right here to combine those together. And again, that's what we're basically doing. We are combining two functions together to create a third function. So instead of 3 times x minus 1, it's 3 times our new input, which is g of x. So let's get that going. 3 times x squared minus 4x plus 8. And then how about a minus 1 on the back? Wonderful. And let's go ahead and clean this out, of course. Looks like I'll get a 3x squared. How about a minus 12x? And I'm getting a 23 on that. I hope you are as well. Okay, good. I'm going to box that up, put that in place, and that's looking pretty good. All right, I'm going to have to do a little erasing here because I'm going to keep drawing and circling things and just want to show you where things go and so forth. So next order of business, everyone, is to take a look at letter B, g composed of f of x. So we start with an input. It goes into the f function, and we get f of x. And here's the key. Now f of x becomes the input of the g function. So f of x is defined for us right here. That is the function. And now that becomes the input, of course, for the g function. So let's go ahead and draw those arrows in. If you get an opportunity to do that, that might not be a bad idea until it becomes really comfortable for you. But again, just function f of x, becomes the input of the g function. All righty. Well, let's see. We're going to have to clean this one out a little bit, but let's at least set it up first. So 4 and then 3x minus 1, and then how about a plus 8? Okay, very good. Would love for you to pause the video for a moment, just being comfortable with the algebra manipulations here. So if you could go ahead and expand that out and combine like terms, that would be great. But let's see what we end up getting. I'll start mine out right about now. So I'm getting a 9x squared minus 6x plus 1 minus 12x plus 4 and plus the 8. So when all is said and done, from my perspective, I'm getting a 9x squared. X's combined together, I'm getting a minus 18x. And put the units together, and I'm getting a 13 on that. All right, not too shabby. That's looking pretty good. So again, let's just sort of be clear about this. Along with the other 4 operations, addition, subtraction, multiplication, and division, composition is just a way to combine 2 functions together in order to create a third function. Okay, good one here. So let's do letter C. And actually, I can envision 2 ways to do this. So if I progress through one way and you're like, oh, wait a minute, I know how to do this a little better, try the other way, and then maybe I can touch on that as well. But what I'm seeing, just independently here, -2 is the input of the f function. So that'll go in function f. And then whatever the answer we get there is the input of the g function, and that would go in place right there. So I'm going to go ahead and start that out. And I'm going to do my little chart here. So basically, -2 goes into the f function. So this one I could probably pull off pretty decently. So again, I start with -2. It goes into f, and out comes an output. So 3 times -2 is -6. -6 minus 1 is -7. Okay, so that would be f of -2. Now we don't stop there, of course, because f of -2 then becomes the input to the g function. So it goes in one more, and I would put -7 in here, And let's see what we end up getting. I'm going to try to do this in my head here. I've got negative 7 squared, so 49 minus 4 times negative 7, so 49 plus 28. I'm getting 77 on that, and 77 plus 8. I'm getting 85. I hope that's legitimate. If you don't mind checking me on that, that would be ideal. And in reality, that's sort of our issue here. We have negative 2 going in, we get negative 7. Negative 7 goes in, and we get 85. And then that seems to be our final answer. Now, I am just curious, did you happen to find another way to pull it off? And I'll give you a hint. Look at your answers from A and B. Well, one of those two. Well, if you look at B, didn't we already kind of find a function for g composed of any f of x? And if you look, that's how we combined the functions together in this capacity. And so as a result, this should be the function rules for any input in order to get an output. So what I'm seeing, everyone, is, and I'm going to just do it this way down below, and I'll be relatively fast, but basically, I already have a function for all of the inputs on g composed of f of x. So all I have to do is perform the function rules on that. So it would look something like this piece right here. And again, I'm pretty confident with the fact that if we did those operations right there, we should probably pull off 85. So we already kind of did the combination function for this situation. And now, again, any input for that combination, we should be able to come up with an output. So I kind of like that, seeing that from both perspectives. Obviously, you go with what works for you, whatever you're comfortable with. Here's an interesting one, I guess, for letter D, f composed of f of x. So sort of a function composed of itself. So this is going to go into the f function. I guess here's what it would look like. Here is f of x, right? So here is the inside piece of our composition. That's looking kind of nice. And again, the way I would verbally describe this is that replaces the input of the f function. So that whole thing goes right in there. Kind of cool the way that works out. And so instead of 3 times x, it's 3 times f of x minus 1. And f of x, of course, is the 3x minus 1. So it kind of loops back on itself. Oh, kind of cool. Let's see, we get 9x minus 3 minus 1. This one's relatively fast, I think. And we end up getting 9x minus 4. Again, if there's any issue with any of these compositions, you're not seeing where they're coming from, oh, please don't hesitate to ask and pause that video. All right, I'll erase that piece. Let's go get letter E and then keep this moving forward. Ooh, good one here. So looks like we're going to start with 3, goes into the g function, get an answer. That goes into the g, going to get an answer, and then that goes into the g. All right, let's see if we can track this one as best as possible. I need to keep myself organized, so 3 goes into the g function. And so let's see what we end up getting here. I might have to do a little mental arithmetic or bring up my calculator on this. But 3 goes into the g function, and we're going to get some type of output. So let's see. We get 3 squared, which is 9, minus 4 times 3. So 9 minus 12, negative 3. And negative 3 plus 8, well, I'm getting is positive 5. All right, so I'm getting a positive 5 g of 3. So that's the first part right here. I'm going to circle this just on the board. That's what we've accomplished so far. That answer, of course, goes into the g value. So now it travels further. It goes into g. I don't know if this is a good way to do this, but I'm going to put a little g right there and a little g right there. So it goes into g once. Now it's going to go in a second time. So 5 goes in. Let's see if we can pull this one off. So I have 5 squared, so 25 minus 4 times 5. So 25 minus 20 is 5. And 5 plus 8, I'm getting 13. Okay, good. So 3 went in, got 5. 5 goes in. Hey, guys, it looks like we're getting 13. One more as I travel outward here. I have to make it go into the g function one more time. And let's see what we end up getting here. All right. I have 13 squared, which is 169, minus 4 times 13, so that's 52. So if you don't mind backing me up on the calculator here just a little bit, that would be great. But I'm getting 169 minus 52, so that's 117. and 117 plus 8. Yikes, I think I've got it, hopefully. Please check me on that if you would, but I'm getting 125. Kind of cool. And if this doesn't help you in any particular way, then find an alternative way to visualize this calculation. But you can see it's sort of just this loop. One, then the other, and you can keep putting it back in, really with no end in sight. But we'll stop right there. So good little review example from Algebra 2, kind of get us thinking about this before we hit the next family of functions. So example 2, everybody. Now we go rational family here, and hopefully we have our bearings a little bit. And there's one little conclusion to be drawn by the time we hit part C. But let's start it out. I'm going to go specific, then general, and then conclude with part C. So f of x is x over x plus 2. G of x is 4 over x minus 1. And it says find f composed of g of 1. So we would start with 1. It goes into the g function. Then that answer will go into the f function. So let's start that out. I'm going to do the same thing. It just kind of helps me initially. So number 1, it's going into g. And so I would do, let's come right over here, 4 over 1 minus 1. And that's kind of interesting because it is the rational family. And I do have a 1 minus 1 in the denominator, which would produce 0. And we do, of course, know that that does not work. So 1 goes into the g function, and unfortunately, we do not get a real number answer here. We get an undefined situation. So I can't even go any further. There's no point in going here because that doesn't work. Okay, so keep that in the back of your mind if you would. That particular input doesn't work on this combination right here. I cannot do f composed of g of 1. I do not get an answer. Okay, well, let's go ahead and combine our two functions though. Using this description right here. So I have two original functions, and I'm going to combine them together to create a third. And we're going to do it by way of f composed of g of x. So let's see, g of x is going to be the input of the f function. I'm going to just do some more circling and drawing, but if it doesn't suit your needs, don't bother. But that's going to go right there and right there. So let's see, I'm going to get a 4 over x minus 1. And that's over the 4 over x minus 1, and then plus 2. When we worked with fractions within fractions, I kind of probably had you do an over 1 situation. You don't need to if you don't want to. But yeah, you're going to have to come back to some of that stuff from the beginning of the semester where we clean out some of these fractions within fractions. So let's test your algebra mettle here. If you would, please, clean that up. See if you remember how. Okay, well, the way I taught it was the supposed shortcut way, and I'll stand by that. But basically what we want to do is multiply all of these fractions, all of these denominators, by the LCD. And as long as I do it on the whole numerator and then balance it out with the entire denominator, that's okay because really this is then multiplying by 1. This over this is really just 1. Kind of cool. And I guess the way we do this is sort of distribute this in. So this is going to distribute in here. And see it, everybody, what happens to those x minus 1s when we multiply this into this fraction? X minus 1s cancel, which is exactly what we wanted. So I end up getting a 4 on top. Okay, good. Now same thing here, reset, and let's do it into these two. Distribute it in, x minus 1 over the times the 4 over x minus 1. Again, those should cancel, and it looks like I do get a 4. So let's be clear on that piece. And then same thing here, I'll reset, and I end up getting 2 times x minus 1. If it's okay with you, I'm going to do this as 2x minus 2. Okay, very good. Now let's see what happens when we combine those together. I'm going to get a 4 on top, and then how about a 2x plus 2 down on the bottom? Okay, just want to be clear on that piece, that is our combination function when we did this particular composition. So I combine those two together, f composed of g of x, and that is what comes out. All right, now here is the key and a conclusion to be drawn. What if I asked you for the domain of our new function right here? So here's our new function. Notice it is in the rational family, and we've worked with domain in the rational family, of course, and we have talked about the prospect of we cannot divide by 0, so anything that would make us divide by 0 would have to be excluded from the domain. And so I'm hoping you would see that if I sort of do this just off to the side, and if you can do this mentally, then don't bother with this, but basically that's the situation. And so when I bring over the 2, kind of get that, and then I divide by 2, I'm seeing that x can't be equal to -1. That would be bad, so to speak. And so here's the situation at this point in time. I cannot have an x value of -1 with this particular function that we created. Now, here's the thing. We're not quite done. Look at part A specifically, and is there anything else there that needs to be included with our representation of the domain right here? If you remember, I tried to do f composed of g of 1. I actually tried a particular input with this combination right here. And notice I didn't get very far, did I? I tried to put 1 into the g function, and I got undefined. I couldn't go any further. So could the 1 as an input here on this particular combination, is the 1 going to get us any type of answer? No. And so as a result, that also has to be part of the domain, that x can't be +1. So the situation at hand here is this. Let me try to explain this as best as I can. We created this function right here, right? We did f composed of g of x. Now that composition, we basically used g of x to come up with this function right here. We used this inside function to create this function. If this inside function has some domain issues, then those domain issues carry over to this creation right over here. And that's the idea. So when we do a composition, we're really using the inside function to make this new function right here. And if this function has issues, then our overall function has issues also. So I guess here's how I'm going to say it up on my board. And then again, if you have some questions to re-clarify this, please don't hesitate. But basically the idea is the domain of the inside function carries over to the domain of the composition function. Okay. Because the inside function was used to create the composition function. And whatever restrictions are on that inside function right here, those carry over to this right here. Okay? Because you're using this to create this. Sorry for being redundant, just trying to emphasize that point. So we just have to be careful. By the way, if you tried the -1 just from here, you would kind of see it. Like we saw it here, f composed of g of 1 simply doesn't work. Now you don't have to do this on your paper, but if I tried f composed of g of -1, we would also see that it doesn't work. What's kind of fascinating about this is if I put -1 in, I would start with -1, it would go into the g function, and let's see, I would get 4 over -1 minus 1. So that would be a -2 down below. 4 divided by -2, that's -2. And then I would try to put -2 into the f function, and take a look right here, guys. Am I allowed to put -2 into the f function? No. And so you see, both ways, both values, starting out with this and starting out with this, eventually produces an undefined. One does it right away on the inside function, and again, that's our conclusion, that the inside function restrictions carry over to the overall domain. So we saw that right here. Stop, we can't do it. And then also, of course, we see, just from here, we see that that wouldn't have worked if we kind of started from the beginning. I would have gotten past at least the first step, but not past the second step. So that's why two values in this case are excluded from the domain. Okay, good. Let's move forward. So the next order of business is to reverse the process. Not sure if you did these types of problems in Algebra 2, but there's some interesting ones. In fact, I kind of like these because we can be a little creative with them. And so what we've been doing up to this point is taking two original functions and combining them together to create a third function. Now what we're going to do is reverse it. I'm going to give you the third function, and you're going to go back and give me the original two. So example 3, it says, write functions f of x and g of x so that f composed of g is equal to h. So here is our combined function. Give me the original two. Okay. So this is all based on the fact that composition, in essence, is a function within a function. And I kind of like this piece. We kind of do this intuitively with a variety of topics in pre-calculus, but I like kind of talking about it in this particular context. So here's what I'm thinking. Look at this function right here. This is a fairly basic one. But basically what I'm thinking is, can you find kind of a function within this function right here? Is there something that you can sort of make by a function by itself that's not the entire thing? Well, I'm sort of looking at that x plus 1. You know, doesn't that kind of look like a function within the function? Well, here it is. Here is the function inside the function. So guys, we're going to call that g of x. So whatever the function within the function is, that's going to be our g of x. Now remember how a composition works. That function replaces the input of the other function. So if I've taken x plus 1 out, then basically what I'm thinking is this has to be now represented as the input, because this would replace the input of the f function. And so if I pulled x plus 1 out, then all I have to do is replace it with x. Now again, the first time is always the hardest, but I would ask you, if I asked you to do a composition f composed of g of x, wouldn't this replace the input here, and wouldn't we get this piece over here? And the answer, I hope, is you would say is yes. So in this particular case, I guess the way I would argue this is the function within the function is g of x. And then whatever we pull out as our g of x just gets replaced with your basic input. All right, well, let's try a couple others. These are quite a bit more comprehensive, and so as a result, there are multiple answers. I would ask us to maybe come up with at least 2 or 3. Well, let's see if we can. So stare at this for a sec. And I guess I would ask you, do you see sort of just kind of a basic function within this overall function right here? I see a couple different options. I'm going to start out with one. I like that 1 plus x squared. That's, you know, a nice looking quadratic, as a matter of fact. Isn't that sort of just a function independently? So let's call that our g of x. And then the question I guess I would have for you at this stage is, if I pull out that 1 plus x squared as our function within the function, what does f of x have to be? Well, as I had alluded to, remember how a composition works. This replaces the input of the f function. And so let's make it now an input. And so instead of 1 plus x squared, instead of 1 plus x squared, we just put an x. And now that's being cubed. And again, if I asked you to do a composition, wouldn't this go right in here? And wouldn't we get this piece over here? Cool. I guess I would ask us maybe, see if you can come up with one more. Do you see another way to kind of pull that off? See if you can pull out something else, either more or less than what I pulled out on this last one. Okay, I'm going to put mine in place. What if I just pull out x squared? You know, that's your basic function, right? Just a nice looking quadratic. Well, what would f of x have to be if I pull out the x squared from this function right here? I'm decomposing it. And in this case, I'm hoping you would agree that I would probably get something like this, because this would replace the input right here. Probably maybe one more out there. I'm going to leave it like that. That's a good one. Let's do letter C one more time. This one, you know, I could see 3 or 4 good ones just right away. Let's give it a try. So it'd be great if you can work ahead of me here. Do you see a function within the function on this that you'd like to go ahead and pull out? I've got one. I'll just do the cubic. How about that piece? X cubed minus 4. And so if I pull out x cubed minus 4, this piece of the overall function, call that g of x, then what would f of x have to be to make the composition work? Well, it looks like it would be 2 times the absolute value, not of this anymore, but of just your basic input, because that replaces the input. And then how about plus 5? And hopefully, there's a lot of good visualization with this. I'm hoping you see this would go right in there, and you get the overall function. Let's try another one. Again, multiple combinations. That's what I like about it. Maybe you came up with one already. How about now include the absolute value part of it? I don't know, just making stuff up here, to be honest. How about something like that? And if I pull that whole piece out, so in this case, look at the function. What if I pull that out as the function within the function, kind of the absolute value family? And then I'm hoping you would see this would just be linear, 2x plus 5. Very cool. Oh, one more for good measure here, might as well. And again, maybe you've got another one up your sleeve. So think of another function within the function. I'm just pulling stuff out, to be honest. I've got, how about now I include the 2 on that piece? Perfectly fine. That's definitely a function. And if I pull all of that out, then all that I would be left with is just now the input. And then, of course, I never touched the 5, so plus 5. And again, the way a composition works, this goes in for here. Got it. Okay, maybe you came up with a different one. Maybe one I didn't see. Cool. So multiple possibilities. That's kind of what I like about this type of problem right here. So see if you can be creative with it. I did some of the boring ones there, but I'm sure there's some other ones out there. All right. Well, let's go do, looks like the last example. And just a decent application. Let's see if we can put it together. So a lakeside city whose economy depends largely on the lake is concerned about the presence of a certain pollutant. In parts per million, scientists have developed a model for the concentration in terms of the population. So let's see, I've got one function right here. I'm going to box that up. Concentration in terms of population. Beautiful. In addition, the city government has developed a model for the population growth in thousands of the city. All right, so population in terms of time, it looks like. Doesn't really say time is, I'm assuming in years. So we'll just go time in years. And here's what I'm looking for, of course. Write a function for the concentration of the pollutant in terms of time. So you can kind of see how this hopefully progresses. I have concentration in terms of population, and I have population in terms of time. What I'm looking for here is concentration in terms of time. So this is going to be our input, and this is going to be our output. Okay, I like it. So I'm going to do this maybe a couple different ways. If you sort of just, you have it, then you're ready to go. So time is our input. And I like thinking about this from the flow chart perspective. If you don't like the visual, then find another way to pull it off. But basically, if I know the time, what's the other quantity that I do know? Well, it looks like the relationships that are given in the problem is if I know the amount of time that has passed, I have a mathematical way to come up with the population. So it seems to me we're going from time to population. Okay, so let's see what that would entail. I start with t. We want t to be our input here. And if I know t, then I know the population. And the population is 1.47 t plus 27.8. Okay, I hope everyone's okay with that piece. So this is the input. This is the output. Okay, now we don't stop there, of course, because this becomes the input of the secondary function. Now population goes in, and the question, of course, becomes if I know the population, what quantity can I get or derive from there? And it looks like the concentration. Hopefully you're all seeing that relationship. And basically what would happen is here is the population function right here, right? That replaces the input of the concentration function. This substitutes in for p right here because that is population. So, oh wow, this looks great. So instead of 2.54 times p, it's 2.54 times this piece right here. And then don't forget that 9855 on the back end. Okay, very, very nice. Now I don't have this on my sheet, so I'm going to go ahead and bring my calculator up and pull this off, but I'm hoping everyone kind of sees that. Some people call the composition functions the substitution operation, and that's basically what this is. I'm substituting this in for p. And we've already had some experience with that, and we'll get some more with that as we progress through this curriculum. So let me see, I've got to do a couple calculations here. You're probably light years ahead of me at this stage, but that's all right. So I have got 2.54 times 1.47. So that'll be our t value, it looks like. I have that piece. And then 2.54 times the 27.8. So I'm going to distribute that in right here. And I think I'm going to add the 98.55 on the back here. Let's get that as well, might as well there. All right, so I'm not going to be able to remember this, but basically I've got 3.7338. So 3.7338 t, and then plus, let me just see what that was again, 169.162. Okay, very nice. And there is our winner right there. So I'm going to go ahead and kind of box that up. C of t equals, outstanding. I like that. So again, basically, remember what happened here. This substitutes in here. If you like that quickly and better, then that's it. That's pretty much the idea. Okay, let's just wrap this notes worksheet up. Part B. Scientists say that the pollutant concentration of 410 parts per million is harmful to vegetation and wildlife. Based on continuing trends, for how many years can the city expect no major problems? So I hope everyone is in agreement when you read this problem that you're thinking this is a concentration and we're solving for time, essentially. Given the outputs, so we're given the concentration here, so this goes in right in here, and I just have to solve for t. So 338 t, and how about a 169.162? Okay, looks good. How about we just go ahead and minus that on over? How about we divide by this and call it a lesson? This looks outstanding. I'm going to have to just come over here, do this last piece. So I'm going to do a 410 minus the 169.162. Just hit enter on that piece, and then divide by 3.7338. I think that was the number that we got from above. Just want to make sure all my numbers are legitimate before going forward. That looks fine to me. And I'm getting about 64.5 years. So t is 64.5. And again, never really said, but we shall assume years. All right, good. Well, if you have some questions on composition, of course, don't hesitate to ask. We'll go ahead and look at some inverses on the next notes worksheet and keep manipulating these functions. Some good algebra that goes into this. Hey, thanks for listening, of course, and again, just don't hesitate with questions.